Okay, good morning, folks. So today I'm gonna be summarizing light and sight. And it's gonna be mostly theory and some calculations. So let's get right into it. First off, let's summarize the plane mirror. As we notice here, this light ray hits the plane mirror. That is the incident ray. Then that light ray is going to refract because once it hits the mirror, it does this. So the light ray that refracts is the refracted ray. But how do we know that it refracts? We have to draw this, which is the normal line, to show that it does refract. Next up, you can see here, this angle will denote the angle of incident. This is the angle of refraction. As written here, the angles between the incident or refracted ray and the normal line is called the angle of incident or refraction. On a plane mirror, angle of incident is equal to angle of refraction. Okay, now that that's over with, let's look at an example of plane mirrors. Our example here is a man, Daniel, buys a plane mirror and installs it in his home. The image he sees is virtual and upright. Real images don't do this because real images are inverted. To further understand this, real images are inverted because real images are made from concave mirrors, which we will cover later in this presentation. This is what a concave mirror would look like. Everything converges to one point, right here, which is the focal point, F. So, we have Daniel in the real world and the virtual upright Daniel. Now, here's the curved mirror. There are two types of curved mirror. So, first, think fast. What do you notice from these two kinds of mirrors? Think fast. Don't pause the video. Let's see what we notice here. First off, the concave mirror. When we have a light ray, it seems to converge to the point that is the focal point F all of the time. For every case, it converges there. But the same can be said for the convex mirror, because it will make a virtual upright image here. This will be your image, which is virtual and upright, because the image will appear behind the mirror and not in front of the mirror. Next up, that is what we noticed. The convergent mirror has the light rays gathering at focal point, making a real image. The divergent mirror has the light rays spreading out, making a virtual image. Next, images from the curved mirror. So we'll be concerning the importance of the negative and positive sign for this slide. If the image produced is virtual, then the distance must have a negative sign, because it is not a real image. Otherwise, use the positive sign. Simple, right? Let's go to the next one. These are the equations for mirrors. First, we have the classic 1 over F equals 1 over S plus 1 over S prime. The notation may be different depending on which teacher you learn from, but I will be using this notation. First, F is the focal length. So the focal length just means how far it is from the focal point. S is the object distance. That is how far the object is from the mirror, and the image distance is how far the image is from the mirror. Next up, magnification. Magnification means how much your image is scaled up or scaled down. It basically determines the multiplier for your size. As you can see, I is the image height and O is the object height. Then you can also use these two in the magnification formula. You could derive these or just memorize them. Next up, the radius of curvature. It is always twice the focal length. This is because concave and convex mirrors, we make them from spheres. For example, the concave mirror has this shape here, and the convex mirror is just the opposite. Next up is the curved mirror examples. So again, think fast. What do you notice from these examples here? How does the size of the image behave as you move the object closer to the focal point? Here's what we notice. As you can see, the image gets smaller as you put the object closer and closer to the focal point until it reaches the focal point when no image is produced. For the first example we see here. Then the second example, the small image is here. That is the object. The image is still smaller than the object. Now here, when we have it at the center of curvature, which is denoted as C, we can see that that makes the image real and inverted, but at the same position as the object. Now this one, what do we see here? We start to move it closer and closer, but it becomes bigger. So it doesn't get smaller and smaller, because this is the only case where it will get bigger. So please note this case, and sorry for my mistake while making this slide. Next up, if you put it at the focal point, everything refracts, and these two lines are parallel. The rays are parallel, so no image is produced. The last example. You put it beyond the focal point and a virtual image is formed from the concave mirror. You can see these lines are spaced apart from each other very much, and they keep distancing themselves away from each other. So you have to consider the virtual world, and the virtual image now appears. Next, the convex mirror. So again, think fast. What do you notice from this example? Have you gotten what you've noticed? Here is what we notice. The image is virtual, upright, and behind the convex mirror. This here is shading the mirror. That means this whole region is behind the mirror. Now, let's do a quick check. Do you understand this so far? Leave a comment down below. Are you up, sideways, or down? Next, the refractive index of light. As we know, the speed of light in vacuum, or c, is 3 times 10 to the 8 meters per second approximately. The speed of light will decrease when density of the medium increases. The index of refraction has the equation n equals c over v. C is the speed of light in a vacuum, and v is the speed of light in any kind of medium. For example, we might have this medium as air, and the other medium is water. The next slide. Fish, apparent depth, and actual depth. A man looks into water and sees the fish as close to the surface. This is the apparent depth. But then, actually, the fish is deeper in water because the human eye tricks the human itself to see the fish as higher up than it actually is. Therefore, that's where the actual depth comes in, and we can use proportions and ratios to calculate where the actual depth of the fish would be. Next, total internal reflection and the critical angle. The total internal reflection means the light makes an angle greater than the critical angle and reflects the light ray instead of refracting it. So, what we have here is the total internal reflection in action. That means it is greater than our critical angle. The critical angle means this angle is enough to make the refractive angle a right angle, 90 degrees. Now the last one we will cover today is Snell's law. Snell's law says n1 of sine theta 1 is equal to n2 of sine theta 2. So, given one of the angles for the equation and the refractive indexes, you have to use what you call the arcsine to find the other angle. So if you wanted the angle itself, you would have something like this. Arcsine of sine theta 1 equals theta 1 itself, because arcsine is the inverse of the sine. Now, another quick check. Are you thumbs up? Are you thumbs sideways? Or are you thumbs down? Leave your comment. So, that's all for this video, and I'll see you in the next one. Have a great day. And please, point out any mistakes that I made in this video in the comments. I will gladly respond and correct my errors in the pinned comment. So, thank you very much. Again, have a great day. Bye bye.